Hey, Alex. Thank you for getting that first assignment taken care of. Here we're going to move on to the next thing on our agenda, which is relationships in quantitative variables. So what we just finished was looking at relationships in categorical data. Relationships in categorical data are expressed in two-way tables, and we calculate percentages. Here we're going to look at relationships in quantitative data, which is going to be a new type of graph called a scatterplot. And literally what we're going to be doing is plotting points. So this is something you already know how to do, but when we do this scatterplot, a couple of things to be aware of, and that is labeling the axes, and on our horizontal axis, we're going to put the explanatory variable on the horizontal axis, and what we believe to be the response variable is going to be on the vertical axis. In this case, we're looking at the relationship between carat weight and price for a sample of diamonds. So diamonds, for example, the bigger they are, the more expensive they are. And you basically weigh a diamond in this unit of measure called carats. And so when we plot the points in here, we can see the relationship that exists. The relationship might be best described here as like an exponential growth curve, that as diamonds get heavier, their value grows exponentially. So there's certainly a relationship here. The heavier the diamond, the more expensive, and it seems to grow exponentially as well. Just like in the last section that we did, there's still the same definition of response and explanatory variable, where the explanatory variable is going to be like the input and the response variable is going to be like the output, or which one we think helps predict or helps explain some sort of outcome. So if you look at example A here, it says the average income and life expectancy in a sample of countries. So one might argue that if you look at different countries around the world, richer countries are healthier countries and their people live longer. If you live in a very poor country, there might be more disease, less qualified doctors, not as good of hospitals, etc. So in a situation like this, my best guess is that they would be using the average income of the residents of a particular country to help explain or help predict the outcome, which would be life expectancy. In example B, the heights of husbands and the heights of their wives in a sample of married couples. So one might argue, if you knew the height of the wife, can you predict the height of the husband? Conversely, someone might argue, well, if you knew the height of the husband, you might be able to predict the height of his wife. Because typically, husbands are a little bit taller than their wives. Typically, not always. So this is an example, in my opinion, where there's no clear distinction, and you could basically go either way on this one. I could use wife's height to predict husband's height. I could also use husband's height to predict wife's height. So that's one of those where it probably doesn't matter which one you have as the explanatory variable and which one you choose to be the response variable. Now, when we're going to make a scatter plot, if we're going to draw one of these from scratch, basically a three-step process. Step one is we're going to label our axes, right? In this case, we have to make that decision on which one do we want to put on the horizontal axis as our explanatory variable, which one do we want to put on the vertical axis as our response variable. Sometimes it's super important, other times it doesn't matter. Like in the husband and wife situation up above, it wouldn't matter which one you chose as explanatory response. But most of the time when we do this, there will be a clear explanatory response relationship. After you decide which variable is going to go on which axis, then you have to think about scale. You have to put the numbers on there. So you have to figure out a scale factor so the data will fit. And then once you do that, you're just going to plot your individual data points on there. So I guarantee you already know how to do this, but if we look at an example, here are the 40-yard dash times measured in seconds, and long jump distances measured in inches for a small class of 12 students. Make a scatter plot to display the relationship between 40-yard dash time and long jump distances. Okay, so again, this is probably one where there isn't a perfectly obvious explanatory response distinction, but because they listed the dash times first, that's probably what they want us to use to predict how far they're going to jump. So one might argue that the faster some kid is, the farther they'll be able to jump. Okay. Now, step one of making a scatter plot is to label the axes. So what's already pre-printed here from Mr. Wenkowitz is he labeled the horizontal axis as dash time measured in seconds. He labeled the vertical scale as long jump distances. Step two was the numerical scales. So scale your axis. So if we look at dash times, the smallest dash time is, it looks to be 5.05, and the slowest kid with the biggest dash time seems to be around 7.25 seconds. So you need on your x-axis numbers to fit between 5.05 and 7.25. So he decided to start at 5 and go up to 7.5 in increments of half a second. So that's not the only way you could have done it, just seems to be a pretty convenient one for that horizontal scale. The vertical axis is long jump distances measured in inches. So the shortest long jump was 65 inches, and the longest long jump appears to be 184 inches. So on the vertical scale, it's got to fit numbers between 65 and 184. So Mr. Wenkowitz decided to start at 60 and go up to 190 in increments of 10 inches there. Last part is to plot your points. So we're going to use the same skills we have for plotting points from, long time ago. 5.41, 171. So we're going to treat that as if it was an XY ordered pair. So 5.41, 171 in there. So 5.4, 171. Now, we're not going to be able to plot these things perfect. I'm going to do the best I can. The second point is 5.05, 184. Then 7.01, 90. Then 7.17, 65, about there or so. 6.73 and 78, seems to be about here. 5.68 and 130, maybe about here. 5.78, 173, maybe up here or so. 6.3, 143, about there. 6.44, 92, seems to be about here. 6.5 and 139, seems to be about there. 6.8, 120, about there. And 7.25 and 110. Okay, there's a scatter plot. Once we're done plotting the points, now our job is to take a step back and basically describe any sort of relationship that we might see in the particular data set here. So we're going to basically have a few things to address. We're going to want to address the form of the association, the direction of the association, the strength, and are there any outliers or unusual points. So in going back up to form, we are going to be in this unit pretty focused on relationships that are linear, but we might see some relationships that are nonlinear in nature, like the one about the diamonds, which showed some exponential growth. Directions is going to be overall positive or negative, kind of like overall, would it be best described with a positive or negative slope? But mathematically, a positive relationship as the values of the x variable increase, the y variables increase along with it. Or you could also think of as x decreases, y decreases along with it. Okay? In a negative association, when the x values go up, the y values go down, or conversely, if x is going down, y is going up. Okay? Strength of our association could be weak, the strength could be moderate, or the strength of the association could be strong. And this is all going to be based upon how close are these dots to making a perfectly straight line or a perfect exponential growth curve or something like that. So in a strong relationship, that means when you look at your scatter plot, the data is very close to making some perfect mathematical form. Straight line, exponential growth curve, parabola, whatever. Moderate is it's fairly close to creating some sort of form. Like it looks linear, but maybe the dots are not super close to making one straight line. And then a weak relationship is you might see like an overall positive trend in there, but the dots would not be very close to being on the same straight line or the same exponential growth curve or anything like that. So here we'd say the data isn't close to some particular mathematical form. Okay, outliers, they're going to be any deviation from the pattern established in 1 through 3. So basically, if you look at a scatter plot and go, man, that value certainly looks unusual, that means that would probably be under consideration for being an outlier. Okay. So here's a couple of examples of scatter plots. So back to that one we started with, over here on the left, we're looking at the relationship between the weight of a diamond measured in carats and the price measured in thousands of dollars. So what we see in these dots is a relationship that has that sort of association to it. So the first thing we want to address is form. And this, by the eyeball, is pretty obviously going to be a nonlinear relationship in there. But the overall relationship is positive, right? As the weight of the diamond is going up, the price of the diamond is going up right along with it. Now, this relationship, these dots are very, very close to forming this exponential growth curve. So I'm going to go ahead and argue that this relationship is in fact strong. Are there any outliers? There's certainly nothing that leaps out at me as obviously being an outlier. Perhaps, that highlighted point right there is based on its weight is a little bit cheaper than we would expect. But in spite of that, it still seems like it's pretty gosh darn close to this overall exponential form that exists in the data. So I don't know if I'd go so far as to call that an outlier. So I'm going to say here that there are no obvious outliers. Okay, but this thing right here is the weirdest thing to talk about because that's definitely subject to opinion, I would think. Now, if we look at the other set of data, this is relating the dash time to long jump distance. What we notice here is this is probably best described as having that sort of relationship in the points. So I think this would best be described as a linear association. It does not look like it's curved at all to the naked eye. Here, though, the relationship is negative. And so that means it's a negative sloping straight line. So as the dash time increases, that means the kid gets slower. That means their long jump distance is getting shorter. So as the dash time goes up, the long jump distance goes down. That's an example of a negative relationship or like a negative slope from your algebra classes. Now, even though it looks like these dots are linear, you will notice that there is some variability here, right? These dots are not perfectly on a negative straight line. There's some variability here. So we could probably argue that the strength here, instead of being super strong, we could probably argue that the strength there is moderate. And by looking at the scatter plot, there doesn't seem to be any freakishly performing students here. There's no one that's a super slow dash time that all of a sudden jumped a really far distance up there. We don't have someone that's really fast that can't jump down in that lower corner. So to me, just like the one on the left, I would say here there are no obvious outliers here either. Okay. And that's all she wrote for this particular lesson. So again, I'm going to give you some practice problems, try them, send them back at your convenience, and hopefully you can get that done relatively quick. Besides that, thank you for listening.